I'm Adrien. I work as a software research engineer at Cohere, which is a NLP startup in Toronto, and we build very, very, very large language models. And I want to try to convince you today of to all add SideNets to your MainNets, which is kind of a facetious title. The true title is kind of, or the point of this talk is really to investigate the richness of representations as they flow through neural networks. So as a prelude, I don't know how interactive this talk is going to be, but because I can't see anyone's screen, but wait, how does this go forward? No. Okay. So as a prelude, it seems pretty obvious that some tasks are really easy for humans to solve. So 2 times 4, you kind of instantaneously click into the correct answer, which is 8, and then find the dog in this picture. You instantaneously click into the correct answer, which is it's in the middle. There are some tasks that are not easy to solve. So 49 times 51, it'll take everyone in this room quite a bit of computation to get to the correct answer, and maybe some like high school algebra. Likewise, if I ask you to find the snake in this picture, it will, in principle, not jump out to everyone at first. You'll probably need to like scan through, do a bunch of computation, and it'll take a while. Actually, do people see the snake yet, or is it still? I can make, okay, I'll make it bigger. Do people see the snake now? No, okay. So it is here. So it's kind of in the center of the screen. But the point that I was trying to make is that there's two kind of, for the same type of task, like visual, spotting an image or spotting an object in an image, human beings take just varying amounts of time to figure out which, like where an object is. And this seems, very different from the way in which current neural networks work. So, so basically, for effectively all neural network architectures, or at least the default and standard ones, no matter the complexity of the task, no matter the difficulty, every single image will be fed through the same set of layers, the same set of transformations. That seems wasteful. Like in general, if a task is simpler, it seems like in an ideal world, the computation would just end fast. And if the task is difficult, then the network would take its time, think things through, and then give an answer. And that's what humans do, obviously. And this becomes kind of particularly pressing as the size and scale of the neural networks that we use grows. So I think this is a picture of a ResNet 38 or 18 or something, which has something on the order of tens of millions of parameters. Imagine this diagram, but for GPT-3, which is hundreds of billions of parameters. Imagine like 10,000 of these kind of all stacked down the screen. And no matter the input, even if you're asking it to do, say, a really trivial task, that computation will be executed. And it just seems like, yeah, kind of silly to do this. And so I like this seems like the kind of more optimal case, where if you give it an easy thing, like where's the dog, it says, it flows through a small fraction of a network and says, here's the dog. And then if you say, where's the snake, it flows through a really large fraction of the network and then gives you the answer. So this seems like the correct way to do things. And it would be also cool if we could come up with a method that does this across modalities. So, a neural network at first, like the input to a network is just a simple thing. It is like a domain-specific thing, like a piece of text or an audio waveform or an image. But all neural networks take those things and turn them into just representations, which is like a list of numbers. And if we can find a technique that just operates in that space on just the list of numbers, then we'll be happy. So there has been past work. These 3 papers, I kind of do effectively that in vision. So the first one like takes a small network and then passes an image through it. And then if the model kind of is not satisfied with its confidence, it'll pass on the image to a bigger network. And then if the network is not if that network is not confident with the answer, it'll pass it on to an even bigger one, etc. This second one kind of has the main trunk and then a side thing, but it's quite a complicated kind of side branch. So like the kind of image will flow through, and then there'll be a side thing that kind of establishes whether or not at this point the representation is rich enough to perform a task, like a classification task. This side thing, it's kind of the way they do it is with genetic algorithms and has a self-attention head, and it's quite complicated. But yeah, that seems to work. And then there's another thing called a cascading neural network, which is the same like trunk idea, except there's a ton of little branches on the side. So yeah, that's the prior work. It's very cool. And that's in vision. And in NLP, we just had a lovely talk about GPT. This is kind of a look at the internals of a GPT. So GPT always predicts the next word over and over and over again. And this plot is kind of a representation of how quickly the GPT kind of is like how so the y-axis is kind of the representations as they flow through the model, and this plot is like how quickly does it figure out like what it wants to say next. And you can see that it quite quickly like zeroes in on the thing that it wants to say. And so this is an indication that probably freezing the computation earlier will not have too much of a deleterious effect on the network's performance. Since it seems like, yeah, a lot of this stuff, it just knows already quite quickly. So yes, so this is the proposed architecture. It is kind of painfully simple. In academia, we have a tendency to want to make things fancy, but in real life, you almost certainly want to change that makes as few you want to I think that's as few lines as code as possible, because otherwise the space of complexity grows kind of enormously, and you have no idea where the bug is introduced, if anywhere. So it's just, yeah, a painfully simple architecture. You have a very standard ResNet, or you have a very standard transformer, and then at some point in that flow of transformer blocks, or that flow of ResNets, you just add a simple feed forward and a softmax, and then so you kind of pass in your input, and then it flows through up until where the SideNet is, and then you pass that representation through the SideNet, and then pass it through a softmax, and then look at whether or not the prediction of the confidence of the softmax is high enough, is like above a threshold that you set for confidence. And if it's higher than that, if the softmax is higher than that confidence, then you just return the input, and then you no longer have to go through every other transformer block or every other ResNet block. And if it's not, then you pass it through the whole model. And this was kind of surprisingly easy to implement, and it worked on the first go. And another important detail: these are trained jointly. So the kind of the MainNet and the SideNet are trained at the same time. And yeah, the losses are just summed. There's no hyperparameter there. It's just pleasant. And these are the results. And so yeah, this is maybe a bit much to absorb. But on the left, you have the vision results. You have the normal ResNet, which is the orange. And then you have kind of what happens when you use different thresholds for the SideNet, and that's in blue. And you can see that kind of there's no, at least in vision, there's no real cost to using the SideNet. And if you slowly, progressively lower the threshold, then you get slowly kind of an arcing decay in performance. But it's pretty undramatic. In NLP, oh, and this is CFAR 10 on a ResNet something, ResNet 50. Or yeah, the different sizes of ResNets. And then for the NLP task, that's SST2, that's a sentiment classification problem. Kind of interestingly, it's the having the SideNet fares worse. But I think or at least worse compared to the ResNets. But I think the general point still stands that this kind of allows you to explore compute performance space in a way that's really interesting. So normally when you have neural networks, you have just one, or in this case, you would have like a ResNet 18, a ResNet 34, a 50, and a 152. And those are the four kind of models that you have. Here, by changing the theta, or the threshold at which your model returned, you can have kind of arbitrary performance to compute trade-off. And I don't know, I think that's just a genuinely cool idea that you can kind of flexibly bounce around that landscape much more easily than just like having a fixed model size. Other noteworthy things, so the SideNets are calibrated. SideNets might be complementary to other compression methods, and training with SideNets does not hurt performance. So these are kind of all big claims. So I'll just go through them quickly with proof. I'm not sure how familiar people are with calibration, but calibration is this pretty desirable statistical property that if you say something has probability P, then that thing actually has to have probability P. So if I say like, so if a weather prediction is calibrated, if it says every day that there's a 75% chance of rain or something for 100 days, and then over those 100 days, there's actually 75 times that it rains. And you can see here that the ResNet is pretty not calibrated, and the SideNet is. So the perfect calibration is that diagonal line. And the SideNet for the NLP model, the Dilbert, is also calibrated, but the Dilbert itself is also calibrated. So there's no real advantage there. But it's cool. It means that if your SideNet says like 50%, then there's actually a 50% chance of the prediction being correct. Also, a note on Softmax. We use Softmax to kind of get the uncertainty quantification. People don't like this, or there's a pretty heated debate. And obviously, Softmax is weird. Like, if you have a detector of trucks and boats and planes, and you give it a picture with a truck, a boat, and a plane, the Softmax would be 1/3, 1/3, 1/3. And then if you give it like gibberish, it'll also be 1/3. So obviously not the best measure of uncertainty, but it's useful. So we use this anyways. SideNets are maybe complementary to other compression methods. So using the SideNet on a Dilbert reduces its average parameter use by 30%, and that costs 0.5 on the task. Dilbert reduces its parameter count by 40% from BERT at a cost of 1.4 test. And so, yeah, it seems kind of like an interesting direction to explore whether, like, how complementary or how orthogonal different compression methods are. Adding SideNets did not decrease total performance, so that was a huge relief. Otherwise, it would suck. But if you train jointly, it seems to have no real effect. And yeah. Yeah, normally people don't say what didn't work. So it's yeah, increasing the size of the SideNet didn't work. That's sad. Ensembling the results from the SideNet and the MainNet also didn't work. That's kind of to be expected. But yeah, kind of. Sorry. And yeah, the main limitation, batching is hard, obviously. So if you have 10 of them and 3 of them you want to SideNet, and then 7 of them you don't, then you have to do some annoying reshapes, and it probably becomes not worth it. So this would be really like the primary application would be for kind of single inference. And yeah, things that are worth exploring further, attaching heads to intermediate stages of the SideNet and seeing how they perform, I think might be an interesting measure, not in terms of practicality or engineering complexity, but just like seeing how difficult a task is, or the richness of the representation as it flows through the model. Yeah, and yeah, I think that's most of what I wanted to talk about.